The, the menu for today is we are going to continue a bit with this production scheduling. We're going to go to some, not too much in depth, we are going to retake that later in the semester, but we want to give some, not only some nice pictures and some nice animation, but also want to give you some tools that you have something to calculate with. Production schedule. And then we are going to go to, after we have done that, I hope that will take only the first hour, or maybe less. And after we go that, we are going to look a bit to the architecture of production systems. Focused, of course, on the offshore part. And I think that's very important. That's something that some of you are having with the course of Sigbjørn Sangesland, subsea system, production systems. But I think it's worth to make the comment here, and from the point of view of our course, some things that are relevant that you have to take into account in our course. Okay, so let's retake a bit what we have seen last class. Let's, if you remember last class, we finished with you had did you have chance to play with this simulator, with this field simulator? You had some free time. You didn't want to watch any TV series, TV movies. So we said the conclusion was that we had, or the bottom line, something that you have to remember is that there are two modes of operating the field, right? What were those? Mode? Okay, mode A or mode B. Okay, mode A we say is a constant rate mode. And we are sure, or the intuition tells us, that we cannot produce, even if it says constant rate, it's not like we can keep the same rate with time forever. But there will be a point where the rate has to be decreased. Okay. Or mode B is where we have we produce as much as possible, as early as possible, and the decline just goes like that. Mode A is usually selected when we have to build a whole infrastructure from scratch, when we don't have anything else to tie in, where no neighboring facilities have spare capacity. Also something very important, mode A is usually chosen for gas fields. That so far we haven't made any distinction between gas and oil, but gas is very important. For gas fields, to develop a gas field, you have to have, it's not like oil. Oil, you just produce it, put it in a tanker, and then you can send it, and you can begin to be like in the Middle East, that you can just go and sell for one camel money and just move the tanker around the world, like in a bazaar. In the gas, you have to have already a commitment. You have to have a sales contract. You have to have a sales contract. You have to already have an agreement with someone that needs this gas, that is going to use it for something, either if it's for a refinery or if it's going to be used for a power station. You have to have already a customer. I think it's the other way, right? Okay. You have to have a customer, and also not only that, but you have to have, if you want to deliver this gas to your customer, to your final destination, what do you have to have? An infrastructure. You have to have a way to transport this gas. So that's why it's kind of a chicken and egg tale, that you need to deliver the gas, you need an infrastructure, but you also to have the justification to build the infrastructure and to transport it and deliver it to the final destination, you have to have a contract, you have to have a customer. Okay. And there are many ways that you can have this infrastructure. You have, for example, the most common, you have a pipeline. just from the field and from the plant. You send a pipeline and you send it to any place where they need it, a power station, or you can send it to any market in Europe. Or you can use, for example, something that is very popular now is LNG, that you take the gas, you liquefy it, and then you transport it in special vessels. That requires some special plant to first to liquefy the gas, and then to vaporize after the receiving, the sending, and the receiving terminal. And it's something very specific. It's a very complex and very sophisticated technology. So you have to be sure that if you do the investment, if you put it there, you have a market for LNG. You have someone that is going to receive the gas. Also the same thing with the pipeline. If you have the pipeline in place, it's not that one day they tell you, okay, we don't need it anymore, just close it and that's all. So usually you want a long-term contract, sales contract that is long-term. You have a customer, the infrastructure, and that's why we usually, that has to be a constant rate, because when you have a, or maybe not constant, it has to be constant rate, but you might have different plateaus, for example. But usually they say we want you to deliver a certain amount of gas for this amount of time that we will need, and you reach an agreement and a commitment with the customer. Is some examples of these type of fields that were relevant and kind of that we have nowadays is the field Snowhite, for example, that is located in the Barents Sea, just 140 kilometers from Hammerfest. And then we have another example is field Edvard Grieg, that might still give nightmares to some of the people here that took language, that were reading the books, I guess. No, Edvard Grieg was the composer, right? Who is the writer? It's another field also, Ivar Aasen, right? Yeah? You should know. Huh? I know we are not in a literature class, but you should tell me, no, you're wrong. Okay? Edvard Grieg is a musician and Ivar Aasen is a writer. Okay? So that field also is operating in that mode. And some here, for example, some fields that will be operating like that. We have the satellite, the Morvin field. That is a satellite to Åsgard. Okay. Now, okay, so there was one thing that I forgot. Yeah, there was one more thing, but I forgot what I was going to tell you, so maybe I will come back later. So for all of these fields you have, it's not exactly like we show the production profile, it's not exactly like we show here, but we have, if we see a mode A field, it's going to have first, the production doesn't start all the way with the plateau rate, but it has some building up period. And building up period usually happens when you put more and more wells and more flow lines in operation. So that's this period that it takes, is called build up period. Okay. Then you have the plateau period, if there is any plateau. If not, you just will have directly from there the decline. But if you have then the plateau period, and then you have lately the decline. And at the end we have what is called the tail production. at this point is where we decide to do the shutdown of the field and the abandonment. And of course, remember that if we don't have plateau, we just short and these two parts meet, and you all the time have a build-up, and then you will have a decline. Now, one thing that I told you yesterday that is kind of intuitive that you have to think, or that you already gave me the answer more or less, is that if I have the same field and I produce it with a very small, the height of the plateau is the rate is very small, so I will be able to produce for a longer time, right? And then I will meet still the decline and it will go down. If I have medium plateau, medium high plateau, a higher flow rate, then the end of the plateau will come sooner. If I have something very big, will come much sooner, and so forth. Okay, all of you had the intuition why this is happening. So let me just put you a picture of the profile. Oh, I have it in the other images. Okay. So you have a bit nicer picture of the drawing that I just made. Yeah, and just before, I'm going to now to start to introduce a small topic, or a small theoretical part, to make a small exercise here in class. So, but before that, we are going to say some rule of thumb to determine the plateau rate. Or just to get a first approximation of what can be, depending on the size of our reserve, what can be the reasonable or more or less in the ballpark plateau rate. Rule of thumb to determine, or to have a first order estimation of the plateau rate. Okay. That if for example, a company has made a discovery of gas and they have certain volume, and then a company, power generation company, comes and says, okay, we want to use your gas to generate, you have to have more or less an idea how much you can supply to them. Or also the same thing if you have an oil field. So the rule of thumb is that the annual offtake for oil fields, the annual offtake is going to be equal to the total recoverable reserves times 0.1. Okay. Every year you're going to take 1% of what you can recover underground. And what are these total recoverable reserves? Any one of you remembers?
How much we can produce.
How much we can, but that is realistic, okay? How much we can take what is in place, from what is in place. So we can say that TRR is equal to what is initially in place, that how you call it, is either initial oil in place or initial gas in place, that's how you find it in some books. Or if you use SPE nomenclature, this is capital N or this is capital G. Or if we want to talk about the two phases indistinctively, we use Q. Yeah. If you're not sure, you're saying the discussion generic either for an oil field or for a gas field. We just use Q. Times the recovery factor. Again, the recovery factor for an oil field, it can change quite a lot, but for example, just to give you some numbers, it was 30%, 27% in 1970, then in 1990, maybe 35% average, and then we are in 2010, we hope, or we are reaching to 50%. Okay. That all depends on the experience, on the type of reservoir that you have, but so the annual offtake, you say, I have to take annually 10% of what I have, of what I can recover from in the subsurface. So we can put the definition here for those of you who don't okay, and that should give you, with that number, if you take every year 10%, we say that this is good for maybe 8 to 10 years of plateau. You still have to make the calculations, okay? That's not like a magical rule that you just do it and then you just assume that that's going to last for all of those years. But that's just the first approximation, just to have an order of magnitude. That's the number that the managers or the people negotiating are using to get an idea. Okay. And then for gas fields, it's the annual offtake is equal to 0.3%, 3.5% of the total recoverable reserves. And in that case, this, as in the case of oil, is G times the recovery factor, and the recovery factor of gas is usually much higher. It can reach up to 90%. But it's much less. If you see the annual offtake has to be much less than with oil. Now, how do I, if I have the annual offtake, okay, that's the amount of fluid that I have to take out of the reservoir in 1 year. How do I get the flow rate? Or how do I get the production rate? Any suggestions? By the number of days, and the number of days will be 365. Are you sure that you will be producing the field for every day in the year? No. So usually you have a factor. Okay, it's depending on the operational days in the year. So the field rate. Let me put it operational days. And that usually the oil companies, they have very good registry, or they have a very good data, or historical data about it. Okay, so they know. Is it too difficult to read for some of you? No. Okay, they have also some statistics, and they know what to put in that value, and that tells you the annual offtake. As you see, it's a volume. This is in units. G is in units standard cubic meter. Okay. And then you divide by number of days. So this is in days. That this unit is in days. So at the end you get a rate, flow rate, standard cubic meter per day. So the units are consistent. Okay, and then very soon we are going to apply this formula. Okay, also before we go to our a bit more technical, also something that you have to take into account is the associated fluids coming with the main production fluid. Okay? That means if you're producing an oil field, you have to take care of, you have to be careful with gas production and also water production. Or if you are in a gas field, or if you have a gas field, you have to be careful with the oil production, or we don't call it actually oil, but we call it condensate production. And water production. And why is that? Just to give you an example, if we say here a plot again with time, and we have certain oil production, let's say that we have the plateau, and then we have gas. Remember that they have different scales, the volumes are very different, but I'm going to put them in the same plot, so you have to use a secondary y-axis. So let's put here, that's Q gas. I'm putting, if you see, that's what, any of you here taking the course of Professor Whitson? No one? Already took it before? Yeah. Professor Whitson, it's PBT fluids? Fluid behavior? Yeah, you're taking it? Okay. So he's using nomenclature, the nomenclature is that Q is flow rate, small q, then you have the subscript indicates the phase that you're producing, and then the bar on top, it means that it's at standard conditions. And then you have the water. For example, initially you have very little or no water production, and then it began to go up and up and up. Yeah. So it's important in the way that if you are producing, for example, you have sized your facilities to process certain amount of oil, gas, and water, but then for some reason it begins to increase dramatically at any part of the field. It might be that when it reaches, for example, water reaches this point, it reaches the capacity or the maximum capacity of the plant. And then you're obliged to reduce your production, okay? Because everything comes together. So if you want to reduce water, maybe you cannot do it by itself, but you have to reduce the flow of all of them, okay? The flow of oil and the flow of gas, and that means that it's reducing your economical income. That the same thing happens with gas, with the associated products. With oil, it's likely that it's not going to happen because you're planning and you're controlling the oil, and you are following the production of oil according to your original plans. But what you cannot forecast very well sometimes is how the gas is, what is going to be the gas production and what's going to be the water production. So let me just put here. And in a gas field is the same thing, but then it might happen something good with the condensate. Let's say that with the gas you have exactly the same, then you have a plateau and then you have a decline, okay? And initially you are having some condensate, so that's helping very much to the economy of the field, and then for some reason it begins to decline. Or also with water. Water in the case of oil is not so dangerous to have it. I mean, it's undesirable, but it's not too dangerous, it's not fatal sometimes to have water in the stream. But when you have water in a gas well, that can kill very rapidly. Yeah, that can kill very, very rapidly the well. So we try to avoid, if we have water, our reservoir development strategy has to avoid at all costs to produce water or any liquid or any significant amount of liquid. Why? Because that can cause very dramatically that the well will lose energy, and eventually die very quickly. Okay, to the life of the well. And also about the processing facilities, if you have initially you were designing them to have a very dry gas, but then all of a sudden you have some kind of wet gas with a lot of liquid, so you have probably to do some changes to be able to accommodate that. And you have also, it can cause that you have some limitation in the capacity, processing capacity. So all the time, look, we are doing a lot of analysis, very simplified, looking only at one phase. But something that you have to take also further is that you have all the time to look at the products. The products, so sometimes in case of gas, the condensate can make a big change in money, but also can make a big change and tell you exactly when you have to shut down production. Oblige you in a way to shut down production.
This decrease in condensate production, is it associated with the gas decrease, the gas production decrease?
It's associated, but also you might have it here. Like if we want to put it more general, we can put it here. And as I said again, this is just an example, but it might happen that you have some kind of drying effect when you are producing the field and when you are taking initially a lot of liquid close to the wellbore, then it gets drier and drier, and then all the time you get less condensate, okay, or get less liquid. But that's just an example. Okay, so that is a reduction in the income. Okay. So now let's go and make a small exercise. First, we are going to use the analogy first of one single well and one reservoir that behaves like a tank. Single well plus a reservoir that we say that behaves like a tank. So first, how did we calculate the rate in that case? What did we say was, we don't have it here, it's the other class. Okay, in the previous class we have said that for every reservoir pressure, you could find a rate. Okay, you can find a unique rate. I told you that the rate that's going through the well depends basically on the drawdown, on the difference in pressure between reservoir pressure and separator pressure. We will go more in detail in that part a bit later, but just in a very early, so that's what you have to have is kind of an intuition, okay? That the Q is a function okay. Q, we say that is a function of reservoir pressure and separator pressure. But this is constant, so really we can take it out of the equation. We say that in a way the rate is just equal to PR. That is if what? What condition it takes for it to be only depending on reservoir pressure?
It's not specified.
No, what else we had in the system that we could change? One thing that is changing with time is the reservoir pressure, but there was something else that we were able to modify, okay? So this is also for a fixed choke opening. If choke is fixed. So we can make, you agree with me that we can make a plot if we find a very good production engineer in our company and we tell him, you know how to use the software, you have a strong background. We hope you are also going to be a good production engineer by the end of the course. But we say for each reservoir pressure, please calculate what will be the rate that this well can produce. So how the guy is going to come up with which kind of plot? How does it should look like?
It will decrease from the very first.
Okay, here is something. Let's say this is a minimum pressure that we have in the reservoir, and then it begins to go up, right? All of you agree? When I have a higher reservoir pressure, that means that the reservoir is very early, is very young, then it has a lot of energy, then it could flow a lot of, then the flow rate could be very high. Okay? But as it begins to decline and decline and decline and there is less material, then there comes a point where the rate decreases very much. Okay? So you agree with me that this is the plot? And this I'm going to say that this comes from, I'm going to call it production engineering calculation. Yep. And of course it depends on the choke. So that curve that he drew is for a choke opening, for a certain choke opening. What happens if I open the choke? Well, how will be the curve? Will it be the same curve?
No.
Okay, how it will be?
The decline will be faster.
Okay, faster. The decline. What does it have to do the choke with the time? Now we're saying at one stage in time, each one of these points is certain reservoir pressure that we have in the tank. What happens if now you have the choke very closed or the choke with a big opening? What you will produce more, right? So let's that's choke opening. Let's say we say that this is 50%, okay, just to put a number. And now if we open the choke, we should get something like that. A much higher. Okay. Yep. Choke opening, let's say that this is and then when it's completely open, I cannot produce anymore. I cannot increase it anymore. Okay, once it's fully open. Please note that here we have nothing to do with time. We know that certain reservoir pressures are reached by every time, but here we are saying nothing to do with time. We are just looking at that tank that we had in the first class. Where is the tank? I closed it. Okay, we're just looking at this tank and we are saying if I have certain reservoir pressure and is high, I will get certain rate. Now I decrease this pressure, I will get the rate that is lower. Okay, now if I have the same pressure but I close the choke, I will have more resistance, so the rate will be also lower. Okay, if I open completely the choke, then the rate is going to be higher. Yeah, without looking yet at the depletion.
Professor,
Yep.
one question. In the graph that you are drawing, you are assuming straight lines, so one phase flow, right?
I'm assuming straight lines to make your life easy, okay? But really it can be can have a different trend. I'm just saying intuitively, and that's I mean it should decline, but you can argue that might be a parabole. That we leave to the production engineer, okay? To see exactly what is the shape. Now we go to the reservoir engineer. Okay, this we talk to the guys with the production engineer. Now we go to the reservoir engineer and we want to say what is the PR versus time. Okay? But really, that's not a very good way, because it depends what happens if I'm producing a very high flow from the tank. Let's say, remember all the time I have my tank example here. Okay. What happens if I produce a high rate? Okay, it's going to drop very rapidly. Okay, but if I produce a smaller rate, okay, the decline will be slower. Okay? So that's not a good way to use time. It's not a good way to describe the behavior of reservoir pressure. So what would be a better parameter to describe reservoir pressure?
Recovery factor.
Will be, if I say the material that I have taken out of the tank. Would that make sense? The material that I have taken out of the tank, if we say NP produced is equal to the integral 0 and T of the rate ddt, rate of oil. Okay. So how much I have taken from the tank, and here I have taken a very little, just put it like that. Okay. Here I have taken only a small piece of the material of the oil that was there in the tank, so the pressure declines only a little bit. Okay, but when I have taken a large piece of the pie, a large piece of the cake that is in the reservoir, then the pressure is going to decline, is going to change a lot. Do you see that? That's clear for all of you? Yeah? So that's a better way to take out the time of the picture, and that's actually what is done in many reservoir studies. To take time out of the equation, they just say they do everything based on cumulative production. Okay? This is called cumulative production. Okay. Now, we see here that this equation of cumulative production involves the rate, that the rate I'm getting it somehow here, okay, and time. Yeah. So let's make a plot. Now the production engineer is going to use that knowledge that it had from the Q to make the plot of Q versus NP. Okay. What happens when there is no fluid taken from the reservoir?
0.
Okay. The 0. What happens with reservoir pressure when there is no fluid taken from the reservoir? Reservoir pressure is maximum, right? Okay. If reservoir pressure is maximum, what happens with the rate?
0.
If reservoir pressure is maximum, let's go back here. If reservoir pressure is maximum, let's say that this is P R initial. Okay, so I get maximum rate. Okay. But then when I begin to take material out of the reservoir, okay, starts to go down. So that's the behavior, the trend of the rate. Okay, and as I told you, depends on the choke. So this is if the choke is fully open. Okay, but if the choke is 50% open, then we have a rate that is greater or smaller than this rate. Smaller. Okay, you got it right now. Now, I'm going to call this line here, choke 100% open, I'm going to call it the production potential. That the production potential is the maximum production rate that my production system can deliver at a given reservoir pressure. Okay, reservoir pressure we can say that is equivalent or is the same with they say is equivalent to certain NP cumulative production, okay, or is equivalent to depletion state. Okay, at the given PR, what is the maximum that I can produce from that well, okay, from that production system? That's my production potential, or also called flow potential. Okay, is that clear? Yeah, more or less. Okay, so we have for every cumulative production, that is the same to say that for each reservoir pressure, I have a line that is defining that's the maximum that you can produce. You cannot go more than that. For the initial reservoir pressure, this is the maximum. Of course, can you produce rates lower than that? Yeah. How do you do it? With the choke. What happens if I want to produce more than that rate?
You have to increase
Separator. You have to reduce pressure of separator.
No, with the same system. I want to produce more. They give me $1,000, okay? Well, not 1,000, it will be too small, but if they give me $1 million, do something to this system to produce more at that reservoir pressure, a pump, okay? Artificial lift. If I want to produce more than that, artificial lift, and then I have a new flow potential, right? Because the maximum production rate that can be with open choke, fully open choke. That can be with fully, for example, pump at full artificial lift, with artificial lift installed. Okay. But if I leave the choke in a fixed position, can I produce in any other rate than the rate? I have only a unique rate in which I can produce, right? The changing in rate, I can do it only if I have some flexibility in the system. If I can move, open or close the choke, that's how can I regulate the rate. Okay, but if I don't have the choke, if the choke is fully open or if the choke is in a fixed position, then I'm bounded. I have to, for each reservoir pressure and for each depletion state, I can only produce one unique rate, right? Okay, so now let's take a break and come back in at 10 or 15 minutes. Okay, 15 minutes. Okay, so we said, let's see at the simple case. Okay, we say our reservoir is a gas reservoir. It behaves like a tank. That means that it's either very small or the permeability, and it has very good communication between all the areas of the reservoir. That's a very idealized case, but you see it's very powerful because what we're going to cover just now. And then we said, we go to the production engineering department, okay, and we just tell him, remember, the production engineer doesn't have to know anything about what has happened in the past, okay? The production engineer just has to say, you just have to give him actually this system, okay? So the production engineer, and tell him what is the reservoir pressure here. Then it will go and it will do its calculation. It will tell you this is the flow rate that you have. If you change the reservoir pressure, then you get another flow rate, okay? And that's why you get this trend that I showed you. This one. This trend that I showed you, that it says if I have a very high reservoir pressure, I will be able to produce a high flow rate. If I have a very low reservoir pressure, then the flow rate will be much less. Okay? And all in between, it follows a trend. We don't care too much at this point what is the trend. You will see later. Later is the idea that you can generate yourself these curves and you can know more or less how to calculate them. And also one warning that I told you is that it depends on in our case we have a choke in the system. And what is the opening of the choke? If it's closed or if it's halfway open, then you have more resistance to flow. Then the flow rate will be less when compared to the case when you have a fully open. Yeah? Now you just change department, you just walk down the hall, and you go to the reservoir engineering department, and you tell them, how is this pressure going to change with time? And remember, they run simulations with time. We want to take time out of the picture, because if we take, like I told you, if we take a lot, the pressure is going to go down very quickly. If we take a little bit, then it's going to go down slowly. So we want to have a number or something that really to take the time out of the equation. And this thing is the cumulative production. This is for oil, okay, NP. We can say GP for gas, or we can say QP if we want to keep general for any of the two phases. Okay, NP, GP, or QP. And that's nothing, if we are looking at certain point in time, that's nothing that the integral of all the rate, okay, from all time from 0 to that time that you're actually analyzing, the integral of all the rates. And that gives you the volume that I have taken out of the reservoir. Okay? Or I could also do the same to say the volume that is left in the reservoir, right? Is that equivalent? Yep. Okay, I could also create another variable that will be, okay, I can say, let's call it A, okay? A is equal to N minus NP, okay, or Q minus QP. The pressure in the reservoir depends on how much material I have in the reservoir, okay? This number is constant, what I have there in place. So the two numbers that I use, this is what is left in the reservoir, and this is what I have taken out. Okay, what I have taken, the two of them are equivalent, right? Do you see that? Yeah. Okay, so in that way we take out the time of the equation and we say the reservoir pressure only depends on how much I have produced, I have taken out, or how much, or put it in another way, how much is left in the reservoir. And that goes from the initial reservoir pressure, maybe we should put, I already put it here, to a minimum reservoir pressure, and that reservoir pressure minimum, I will achieve it when I'm going to abandon the field. I say at this point in time, when I reach this cumulative production ultimate, I'm going to stop production and I'm going to abandon the field, shut down and close the field. Then I told you, okay, let's now combine the two in one curve. This one depends on reservoir pressure, but also I can put it in terms of cumulative production. It's exactly the same. Okay? If I haven't produced anything, reservoir pressure is very high, the reservoir still have all the material inside, the pressure is high, so I can produce a high rate. If I have produced already a lot, let's say that this is the ultimate cumulative production, then the flow rate that I can deliver is much less. Okay? Then I introduce this concept about production potential. Production potential is the maximum production rate that my production system, and in here you can understand production system has, if we are talking about, in our case, a single well, you know, it can be well plus pipeline, okay, plus separator, or it can be a network, it can be a combination, a group of wells. Okay. The maximum that my production system can deliver at the given reservoir pressure, and we say that all of these are equivalent. Cumulative production or depletion state of the reservoir. And I give you here the warning also that that's when, in our cases, when we have fully open choke. If we have artificial lift, that's where we are operating at maximum. The artificial lift, for example, a pump or a compressor is giving the maximum pressure boost in the system. And you can have some other cases. We are not going to go, later we will go into these details. And also one small thing that I wanted to bring your attention to was that not only in the most general case, let's assume that you have now the same tank, but now you have water injection, or you have some other kind of injection to keep the pressure. Then the reservoir pressure won't be anymore dependent only on what you have taken out, but also on what you are injecting, you are putting inside the system. Okay? But we are keeping it simple, and we are just neglecting this guy for now. That is good, you know, good enough for many cases. So now that we have this curve, okay, let's say that all the time I want to produce at the maximum potential. I want to produce with open choke. How do I calculate the curve? Okay, let's say case 1. I'm going to produce all the time at production potential. Okay, I don't care. I'm going to produce as much as possible, as quickly as possible. How do I calculate how do I estimate the production schedule? That means, how do I estimate the curve Q versus time? Having this curve, having Q, let's call it the production potential, let's call it, so it will be distinct, QPP, okay, production potential rate, having QPP versus GP, our case is gas. How do I calculate it? Any of you have any ideas?
You have to have reservoir pressures with time.
Okay, so we go to with time. Let's go to those of you, I hope you brought your computer. You go to the course, it's learning. Now you go on the left menu. You go to class notes and videos. Then you see you have a folder for today, 12th of January. And then you have one unique Excel file there. Just download that to your computer, and I'm going to open it here on my computer. I have given you here, already I have done the homework. I have been to all the departments in the company, and they gave me, here you see gas cumulative production and reservoir pressure. So that's the plot on the right that we talked before. And I went to the production engineering department with all of these reservoir pressures, and I told them, please give me the production potential. All of you are in this page? Yeah? Okay, so these are the curves exactly that I showed you before. And from there I told you, let's see if we are going to produce all the time at the potential, let's see how the Q versus time is going to look like. Remember, that's very important, because even though we are working with cumulative production in real life, we need to calculate the economy of the field, we need to do NPV calculations, so all of that has to be based in time, okay, not on cumulative production. Okay, so that's why we have to do the transformation. Let's make that comment here. NPV, cash flow, okay, cost and revenue is calculated time based and not QP based. So my proposal is to look at the equation. Let's look at the equation. GP is equal to the integral from 0 to, let's use a time star, and it's the Q of gas, okay, or Q. Here is, remember, I'm going to be producing all the time, in the more general way is QG times dt. GP, cumulative production of gas. And we are saying that QG is all the time equal to QPP. Okay. Now, if I have a collection of points, I think you have to see, how do I solve an integral with a collection of points? If you see back there in kindergarten or preschool, how do I have, if I have a collection of points, how do I calculate an integral? You remember that?
Use that. On every point you will use an integral and sum them.
Okay, so let's see the curve, for example. We have GP versus QPP. Okay. And if I want to calculate, for example, this section here, this area, what rule did you remember that we used in kindergarten to calculate the area? Huh? Trapezoidal. Okay, so what does the trapezoidal say? Well, let's put numbers here. Let's say QPP of I minus 1. And then QPP of I. Okay, and here we have GP of I and GP of I minus 1. Right? We're saying that the I point is here. And how do we calculate now the area? Because actually what we want is the area, right? So we're saying that GP I minus GP I minus 1 is equal to equal to, what was the formula of the trapezoidal integration? H over 2? But that's not trapezoidal. That's if we are assuming that this is like that, right? Okay, let me give you a help. This is equal to Q PP I plus Q PP I minus 1 times delta T, okay? Times the time at I minus the time I minus 1, right? Let me change the scale here. This will be time. Okay, to avoid any problem, we go to very quickly to Wikipedia.
You just divide by 2.
We have missing, and it says to calculate the integral of a function has to be equal to the difference. Okay, that's what we have in time. The difference in time. It's a bit too small. Okay, the difference in between the dt, in this case we have dt, right? So it's time I minus time I minus 1, okay, multiplied by the rate in I plus the rate in I minus 1 divided by 2. Okay. And that gives you the cumulative production in I minus the cumulative production in I minus 1, only that segment. Okay? Is that clear? Yep. So now, but really, what do we have? What points do we have from this equation? Okay, that we have just put in discretized. We have discretized the integral. Okay, what do we have? What do we have in this equation? We have everything, right? We have GP, we have the potential, okay, and we are missing this time. Okay, so we have to clear from this expression the time. Okay, so let's see, GP time I is equal to 2 GPI minus GPI minus 1. Okay, is that correct? Yeah. So let's now go ahead and using our Excel sheet, let's do that formula. Let's execute that formula. Okay, I think it's okay. So to find out the time, let's use the units that we want to use, that is years. The first time when you haven't produced anything, we have to start from a starting point. Okay, what will be that time? We are going to call that time 0, right? And then the next time is going to be exactly the formula that we are saying. Let's put it to the right so it will be easy to copy. So that's equal to 2 times this cumulative production minus this cumulative production, okay, divided by 1 rate, the potential plus this rate, and all of that plus the previous time. Okay, but remember, first look at the units. What units is that expression going to give me? Let's make a simple analysis here on the left. Okay, this part, the upper part, is in volume. It's a volume unit, standard cubic meters, and this unit is in flow units, standard cubic meters per day. So when I divide them, that's going to give me in days. So to change it to years, I have to divide by 365. So all the expression I divide by 365. Okay, and I add to the previous time. Okay, and it told me that 2 years had happened until I reached this reservoir pressure. Okay, then I drag it down, and I'm going to obtain, let me just put it this in years so we don't need all of these decimal points. So what are we doing? Just not keep this perspective. We had the production potential versus cumulative production, and we know that there is an equation that relates the two of them, and it's a very simple equation. It's just an integral equation. And then we said how from a collection of points we can calculate the production profile, because the production profile is the most important indicator of the performance of the field. So we found something a bit, tricky, but easy to understand if you go back a bit in time. And we said, okay, with this one we can calculate exactly at which time I'm going to be producing which rate, which production potential rate. Okay, so let's see how that looks like. So it looks like that field with that well will be producing for 143 years. Okay, so let's plot it to see how it looks like. So it's here, insert. Okay, is everyone okay? Following okay? Yeah? E, and this is, we want to plot is C. Okay, and that gives you exactly what I was expecting. If we leave the choke at the open position all the time of the field, what should I see? What should I expect? Just a decline, just smooth, just like what I was expecting. And in this case, it's for 140 years. Why is so long? Why? What is it indicating? That the reservoir might be too big to drill only one well, right? That if you want to produce it quicker in a time frame, that human time frame, let's say 20 years, 30 years, so I have to put more and more wells to be able to drain more from the reservoir, right? Okay, so let's put that. I'm not also something for the exercises. I don't like a plot delivered like that. You have to move it to a new sheet and put here Q versus time, and all the time Q versus time for the case open choke. Okay, so you put it in a new page, and now you begin to do some changes. You first put increase the size maybe to 16 or 18, something that it can be good to see. So then you put in bold, and then you put the chart titles. So here we have a well rate, well gas rate. Yeah, and this is time in years. Okay, and probably I can increase also the size of these points, so they will be a bit more visible. Marker options. Okay, so that's how I produce the well. If I'm producing for for only one well with open choke, and gives me the trend that I want. Let me just take a snapshot of that. Now what happens if, let's say, I want to produce the field with a constant rate. I want to produce the well with a constant rate. Put that here. Okay. Now I don't want to produce at the potential. I want to produce at values lower than the potential for some time. How do I find for how long I will be able to produce that rate? Okay, let's say that I want to produce, now first, one question, and that will be for homework. A value of, here we're getting 10 million standard cubic meter per day gas rate for one well. Is that a good number, a bad number? Does that tell you something? Anyone?
1 million?
10 million. We're getting 10 million. You have to find out if that number is, that yourself is your homework, okay? If that number is a very big number, is a kind of a normal number, if it's a low number, okay, you have to find out. That I leave you like a homework, not graded, but very important for your professional life, okay? But now let's say I'm going to say, what happens now if I don't produce like that? Okay, I don't want to produce like this at all the time open flow, but I want to produce at 4 for a plateau, the value less than the potential. For how long I will be able to produce it? So how should I do that? Any suggestion?
So just put the numbers first.
Well, I will be able, let me just make the other two plots, okay, that we didn't put. Okay, so here will be PR versus cumulative production versus GP. And then we have, oh well, we just put one plot really. We just say QPP, okay, production potential versus GP. And GP was A, and production potential was C. Okay, and that gives me that curve. Okay, so for how long I will be able to produce that rate, to produce the rate that I said, 4 million. If you look at the plot, it tells me I'm able, for all of this up to this point, from all of this cumulative production, I will be able to produce rates equal or higher than 4 million, right? But after this point, after this cumulative production, after this reservoir pressure, I won't be able anymore. Is that clear?
Yes.
Yeah? Okay. So how do I calculate the duration of the plateau?
But if, for example, if you decrease the rate and if you make it constant, then it will extend this period.
Okay, let's say, but it's not just I say from the plot, okay? Let me just take now That's not production rate, but that's production potential. That's production potential. We can call it gas production potential. Oh, and that's not time. Oops, have to fix that. That's cumulative production. Okay, and what are the units of that? Standard cubic meter. Cumulative.
So we just divide this by the rate that we would like to have. So
Okay, exactly. So this plot is very important, and you have to be able to know how to use it. You know, we will see now that using this plot is not, or later in the semester, it's not, for some cases it's not accurate enough, and for some cases we have to do something more complicated. But when we are at the start phase, when we don't have much information about the system, this is a very good way to find some initial approximations. Okay, this is a very good and accurate way. Okay, so according to our production potential curve, let's say we wish to produce 4 million standard cubic meter per day from the well in Plateau in mode A mode. For how long? What is going to be the duration of the plateau? Calculate so we come, like you will said, we come to this plot and we say to 4, so I will be able to maintain, I will be able to give, the production system is able to give that rate up to this cumulative production. So up to here, up to this reservoir pressure, GP star or PR star, the production system, the well, is able to provide the rate that we want. After that, no. After that, I cannot not even open choke. I cannot provide the rate. So that's how I calculate. I just calculate the plateau by taking this GP star, the duration of the plateau, is just equal to GP star divided by the rate, plateau rate. Okay, of course we want to take it in years, so we multiply it times 365. That's the number of days in 1 year. Okay, so how much is that? If you go now to the Excel sheet and you look at the data, so we are looking for 4 million. 4 million is here. Okay, we are going to say more or less that's the value that we want, and this is the cumulative production. So we make the calculation here. Plateau duration for 4e to the 6. Okay, and that's equal to this value divided by 4e to the 6. Okay, and at the same time I have to divide that by 365. Okay, 94 years. Now, how do I plot that? How do I plot what happens after that period? Any ideas?
Starting from
Okay.
the rest of the data, from 4 e to the 4.
Okay, so let's first wait. Let's put here, so 95 years of plateau.
Yeah, the next one will be 96.
Hmm?
the next one will be 96.
Okay, years. But what rate is going to have?
3.75.
But why are you so sure? We haven't produced, after that point we cannot produce anymore the same rate. So that, okay, let me just show you how the plot is going to be for that case. Q, okay, versus time for plateau of 4e to the 6 standard cubic meter per day. So it looks like that. We know it's constant, and we are able to produce it up to 94 years. But what happens after that? After that, I will be producing all the time at the potential, right? So I have to do the same thing that I was doing for the potential case. I have to follow, I have again to use the same equation, right? And I have to continue calculating the rest of the points from there. Is that clear? Yeah? So how do I do it? So we are here in this point, okay? This point is just fixed rate. So we can put here, we say here that's for producing at QPP all the time. And now we are saying plateau production. And plateau production, I have to substitute. Okay, let me just take that away. For all of them will be 4 million. Okay, so I'm going to put here 4e to the 6. Up to this point. And the time is going to be, okay, so the time here is 0. Sorry, years. Okay, I'm going to take, here the time is just 0, okay, the first time, and the second time is equal to what I have been producing before, right? Well, we can use also the trapezoidal rule, right? Or not? Well, we can just put it simply. We say this is what the cumulative production divided by this rate and divided by 365, right? Okay, that will be in 4 years, 5, 6, up to here. Okay, 94, 95 years. Okay, and after that we will be obliged, the rate won't be anymore 4, but we will be obliged to follow the production potential. So in that case I take this value here. Okay, I drag it all the way. I'm following from that point on. I will be following the production potential. But now to find the time, what do I have to do? I have to use the same equation that I was using here. Okay? So let me copy that equation, or maybe it's better that I do it from scratch. So that equation is equal to the previous time, right? Plus, you remember the equation? Can you help me there? Look on the notes. Okay, 2 times this rate plus this rate. Oh, no, is divided by the rate, right? So it's the cumulative production in this position, which is this one, minus the cumulative position of the previous, divided by the rate, like that, and divided by 365. Okay, because this is giving me in days, so I have to divide by 365. Dividing by parentheses 365 times okay, so now I plot in the same, where is it here? Open choke, Q versus T. We can rename it, say Q versus T, and now I will put a legend. Okay, and I will add a new, and that will be for plateau of 4e to the 6, and the values in x are the time here, okay, and that's how it looks like. Okay. If I produce all the time at open choke, the choke is fully open, this will be the production profile. Now if I produce, I say I want to bound it, I want to choke it to get all the time 4 million, I will be able to produce for a longer plateau, for a long period of time, up to 95 years, and then I will follow these designs. And all of them came from the same curve, okay, from the same behavior. You see exactly from the same. I only need this curve to generate these two curves. And then I can assess what has to be, what will happen if I change the plateau height, for how long I will be able to have it. Okay? Now let's see here I prepare something for that I say, okay, that's really, to develop this field with only one well, that's not realistic, okay, because it's a very big field and we don't want to produce it only with one well. We will take a lot of time to produce it. So we want to produce it with several wells. Okay, and we want to produce it, we can use here the rule of thumb that I was mentioning before in the class. Okay, we have that development. We have what are the initial gas in place. Okay, so we multiply times the annual offtake has to be 0.35 for a gas field. And from there we know, we have an idea what will be the rate of the field. So should I do it here, or you're going to do it at home? Or you're going to get it like an exercise? You choose. You do it here?
Yeah, we do.
We take a break first?
Yeah.
Okay, so let's take a break.